So, acidic and basic solutions, all right, we've heard that before. What exactly does it mean for a solution to be acidic? And the most obvious answer would be an acidic solution is a solution that contains an acid, all right? And while adding an acid to water definitely makes it acidic, all right, the definition of acidic or basic actually has to do with something a little different, all right? So, to understand what it means for something to be acidic or basic, we first need to understand something a little bit about water, and that's what's called the self-ionization of water reaction. All right. So even though we think of, like, if you had a glass of water, you might think it's just 100% H2O. All right. That would not be totally correct, because every once in a while, essentially one water molecule says to its neighbor, they don't really say this, but it's like they say, can I temporarily borrow an H plus? All right. And this is just something because of the properties of water. A lone pair on an oxygen has an ability to accept a hydrogen, but the hydrogens on the water have an ability to get donated, all right? So if every once in a while, this reaction right here can occur, all right? And so I'm using these electron pushing arrows to show this. An electron pair on this oxygen can make a bond with this hydrogen, all right? And the electrons that are in this bond can go and become an electron pair on this oxygen, all right? So essentially, this is a way of this water molecule accepting an H plus from this water molecule right here. That means this guy is acting as a base. This water molecule right here would be acting as an acid. All right. So if that happens, this water molecule would become this guy right here. All right. Notice before it had two lone pairs. Here it only has one. All right. And that's because this lone pair, the electrons in this lone pair, are now the electrons that are in this covalent bond. All right. Notice that that now puts a formal positive charge on that oxygen. And on this guy, since it lost that H plus, but it also gained another lone pair. So the two electrons that were in this bond become a lone pair on that oxygen. That's why we show 3 lone pairs on it, and that puts a negative formal charge on that. All right, so the names of these guys, this guy is, the formula is shown often as H3O plus. This is OH minus. Their names are hydronium ion and hydroxide ion. Yeah. So there's another way you can express this, and I should have drawn in a double-headed arrow right here if you could just do it as formulas right here. But the thing about this is very temporary. Even though this happens, this water molecule accepts this hydrogen, but it very quickly loses that H plus. All right. So again, a couple things about this. Reaction. All right. It happens very infrequently. All right, so at any given point in time, this reaction is happening to only about 2 out of every 550 million water molecules. All right. Secondly, is that it's almost immediately reversible. As soon as a water molecule grabs an H plus, it gets rid of it. All right, and it could either give it back to the water molecule, to the hydroxide, or it could just give it to a different water molecule. All right, but it's not like whenever something when a water molecule grabs onto an H plus, this thing doesn't exist for very long. All right, this is it will have a very short-lived life. All right, it's kind of like a little, you can kind of think of it as a little game of hot potato. All right, where if you had 10 people sitting around and you had a hot potato, at any given point in time, somebody's got it, but no one wants to hold on to it for very long. All right, so So how does this affect water? All right, I'm just going to use a little analogy. We're going to use handshaking. All right. So if I were to say, just like, take any 2 people in the world and say, what are the chances that they are shaking hands right now? All right. If you just pick 2 random people in the world, the chances are very, very low that they would be shaking hands at any given point in time. All right. So does that mean that no one is shaking hands right now? Well, let's think about how many people there are on Earth. There's about, I believe there's over 6 billion people on Earth. All right. So if you have a population that's large enough, even if there's a low probability of any 2 people shaking hands right now, if you have a really large population, there is a high probability that at least somebody is doing it right now. All right. So just statistically, Chances of any two people doing it, very low, but the chances of someone somewhere doing it right now is very high. Okay, so just think about two neighboring water molecules, like these two people standing next to each other. All right, the chances of them doing this reaction, the self-ionization reaction, right now are very low. However, since the total number of water molecules in any sample of water is going to be very high. So, for example, if you had a cup of water would have about 10 to the 25th water molecules. That is a huge number. It's I can't even give a word to it, but it would be 1 with 25 zeros after it. All right. So if we said that this reaction happens to only two out of every 555 million, even though that number sounds really large, it's a pretty small number compared to how many water molecules there are in that cup. So it is a statistical certainty that there would be around 6.02 times 10 to the 16th. Actually, I'm going to change this a little bit. This is all, I say cup, we're going to say this is out of a liter. So change that word right there, cup to liter. So that would make this all correct. So, in that liter of water, there would be about 6.02 times 10 to the 16th H3O plus molecules in the same number of OH minus molecules. All right. So, I mean, that sounds like an incredibly high number in that liter of water. All right. And the thing that's hard to believe about that is the way that we get this many H3O pluses in the water is because of something that happens to only 2 out of 555 million of the water molecules. All right. So, so even low probability events have a high probability of happening if you have a large enough population. All right. So the overall result is that there is a natural, I believe that's spelled, amount of H3O plus and OH minus even in pure water. All right. And these aren't impurities in the water. They are chemical species that exist there because of the basic behavior of what water always does. You cannot prevent this from happening. All right. Even if you were to be able to magically remove all of this from a liter of water, a second later there would be a lot of these around just because the water would make it all by a natural process. So the way that we always describe the amount of H3O plus and OH minus in water is by their molar concentrations. All right. And we express this by putting square brackets around them, and you should know that anytime we do that, we're talking about the molarity. All right, so this would mean the molarity of hydronium ions. This would mean the molarity of hydroxide ions. And in pure water, what we're going to find is that the molarity of H3O plus is going to equal the molarity of OH minus. All right, and the reason for that is if you look at the self-ionization reaction, for the same reaction that creates one of these also creates one of these. All right. So that's why you're going to have that relationship. All right. Something that we know about all water is that the amount of H3O plus times the amount of OH minus is always going to equal a constant. All right. And typically that constant is given as 10 to the minus 14th. That is not entirely true, but the name for what this number represents is what's called the ionization constant of water, but it's represented as Kw. All right, so the Kw of water at room temperature is given as, so what it represents is the product, which is the two things multiplied by each other, and it's 10 to the minus 14th. All right. So the thing about this is that there is a temperature dependence on this. All right. So the reason that we tend to say that it's 10 to the 14th is we're typically talking about water at close to room temperature. All right. Most water that you're going to deal with, unless you've chilled it down or heated it up, is going to be about that temperature. So the specific number would be 1.01 times 10 to the minus 14th. At that particular number, at that particular temperature. And notice that that is very, very close to 10 to the minus 14th. So that's why a lot of times it's just for simplicity, simplified to that number. All right, but notice if you chill that down to about 0 degrees, that this product right here, if you take the amount of this times the amount of that, is going to be lower. All right, it's going to be 0.114 times 10 to the minus 14th. So it's not, there's not nearly as much. So what this means is that this reaction right here happens less in cold water. It happens more in warmer water. All right, but regardless of whether it's cold or warm, it still happens. It's still a very, very small. It's going to still be very small in relationship to the total number of water molecules that are present. So if you take a look at this equation right here, what it essentially says is that this thing times this thing is always going to be equal to the kW at that particular temperature. All right. So using a little bit of math intuition, whenever you have a formula of this general form, all right, A times B equals some constant. And we'll just use 100 as an example, some number that's always going to stay the same. All right. What this means is that if one of these goes up, the other thing has to go down. All right. So because of this, I think it's very easy to think about the relationship between H3O plus and OH minus, kind of like a seesaw relationship. If one side goes up, the other side's got to go down, and vice versa. So whether water is either acidic, basic, or neutral, even though, yes, adding an acid to water would tend to make it acidic, but the reason that it's actually considered acidic has to do with the relative amounts of these two things that are in the water. All right. If water is slightly acidic, it would have slightly more H3O plus than OH minus. If it's extremely acidic, it's got way more H3O plus than OH minus. All right, and the opposites would be true. So here's a graphical way of representing this. Okay, let's start off with pure neutral water. All right, we would have equal amounts of both of these guys. All right, so let's say that we added a tiny amount of acid to that. All right, if you add a little bit of acid, all right, and let's recall what acids do. What makes something an acid is what happens when it reacts with water. Well, acids tend to donate hydrogens to water, and so that ends up generating some H3O plus. All right, so when you add a little bit of acid to water, what you're doing is you're adding a little bit of H3O plus. Right, and if you add a little bit of H3O plus, the amount of H3O plus goes up, and because of that KW reaction, where one thing times the other always has to equal a constant, if the amount of one of these changes, the other one's got to change in the opposite direction. So if something is slightly acidic, that means there's a little bit more H3O plus than OH minus. All right. Well, what would happen if we added a ton more of acid? All right. If you just added a lot of hydrochloric acid to the solution. All right. Well, that would continue to add more and more H3O plus, and that would continue to get rid of some of the OH minus that would naturally be present. And if this were the case, you would consider that solution to be extremely acidic. All right. The opposite can be said if we add a little bit of OH minus. And so an example of something that would tend to add OH minus would be if we added sodium hydroxide. All right. That is a source of hydroxide ion. You would get slightly more of this. That would be slightly basic. An example of that would be something like soapy water. All right. Again, the slightly acidic, an example would be something like orange juice. Something that's extremely acidic, I haven't got it written down here, but something like battery acid would be extremely acidic. Okay, but if we just continue this process, going from something that's slightly basic, if we added lots of OH minus, like if we just dumped a lot of sodium hydroxide into the water, all right, you're going to have way more hydroxide and not quite as much H3O plus. And that's going to be extremely basic. And an example of that would be something like Drano, which is a common chemical for getting rid of clogs in water lines.